Bismillah ar-Rahman ar-Rahim. Today we will discuss electricity. I try to minimize it as much as I can. First of all, static electricity and electrical potential. The word electricity was derived from a Greek word from ampere. Rubbing ampere against another material can lead to transfer of electrons. So if we have materials such as plastics and rubber, and they are being rubbed together, electrons are being transferred from one to the other, and this is what we call static electricity. Of course, it occurs in chemical reactions as in batteries and in biological tissue. This creates what we call an potential difference. Conductors as insulator and semiconductors, of course, the difference between them is the easiness of a transfer of electrons. Of course, conductors as metals and carbon are very good conductors of electrons. Of course, other insulators are definitely the electrons are stable; they cannot be transferred. Regarding semiconductors, we need a slight energy so that this electrons can be transferred, as that present in thermistor, transistors, and diodes. So we need an extra energy for them to pass. As an example, in thermistor, which is a device to measure temperature, as the temperature increases, more electrons escape from. This increases the conductive process, and this measures electricity. Of course, excessive heat will affect the performance of the components of the anesthetic monitors. If a photoelectrical or photo detector is a special type of a semiconductor in the form of a resistor or diode or transistor. When these materials have a radiation falling on them, electrons of this substance absorb some of the energy of radiation, and electron can move, increasing the current. A magnetic field, of course, if we have a conductor with a current flowing through and we oppose it to another one, a magnetism occurs. Some substance by itself are capable of inducing magnetism, as iron. Magnetism is due to sum of many minute currents from the motion of the electrons. This is how magnetism occurs. The region where the magnet can possess its force is called, of course, magnetic field. If a wire is being wound into a coil, and this, of course, will create a magnetic field, and this strength will be increased whenever I put a ferromagnetic material as iron in the middle of this coil and move it. This will increase the process of magnetism, and this is the way how we create electricity. The term magnetic strength, of course, is being this is created in vacuum. Whenever I want to I define the magnetic strength, so I define it in a vacuum. Magnetic flux is greater than the original magnetic strength. It's expressed in some sort of electromotive force, a volt, you see. Of course, is increasing the ferromagnetic materials. The unit of the flux is the Weber. The unit of magnetic density is Tesla, is a known inventor, being Weber per square meter. The magnetic flux density is produced in air by the Earth's magnetic field is approximately 60 micro Tesla. Direct and alternating current, as you can see in the figure, the direct current goes in one straight line, whereas the alternating current, as you can see, it creates sine waves going upwards, downwards, as you can see. Of course, sometimes we have a combination of both of them. the ampere and the current measurement. The ampere, the unit of current is in the systemic international system is the flow of 6.24 times 10 to the power of 18. We'll try to remember it with the Avogadro's number, which was 6.022 time 10 to the power of 23. This amount of electron passing point is the definition of ampere. Suppose we have, as we can see, a magnetic field, and we have a coil of wire. This coil is supported in jeweled material, and this is supported by a spring hair through to counteract the turning effect of this movement of the wire, as we can see. So whenever current passes through this current, this will be deviated along this magnetic field. This will create a potential, and the current will be changed by a pointer on a scale. This is the way the galvanometer works whenever the current goes through this metal. The electromagnetic flow meter will be shown later in the next slide. Simply, it is the fact that whenever current passes through, for instance, the RBC through a magnetic field, it will create a current. This current will be recorded by two electrodes on both sides of this flow, and this movement will be recorded as a flow. See, this flow, of course, it records the velocity mainly. This velocity, of course, is affected by the diameter of the vessel. So we have an average velocity, and the flow meter must be calibrated so that we can get a proper proper result. This is the figure of the magnetic field. As you can see, electrical magnetic field. This magnetic field, whenever it is alternated, it gives a better result. And this is the flow of the RBCs of whatever we want to measure the cardiac output through this magnetic field. This flow is creates a potential. This potential is perpendicular on the magnetic field and the flow. This is the way where we can measure the flow of any vessels and in addition the cardiac output, current flow, and energy production and the volt. Whenever a current flow, as we said before, it creates heat and light and energy. You see, in emergency, of course, the direct current we use as in the operative theater creates an energy. This supposed energy creates a work of 96 watt or 96 joule per second of energy. This is the units of energy per second. You see, in order to drive electron currents, a potential must be present. You see, the unit of potential is volt, and we express the volt here in this definition by energy production and current flow. So the voltage is defined as the potential difference which produces a current of 1 ampere in a substance when the rate of energy dissipation is 1 watt. So we have a flow of current. This current creates an energy of 96 watt. So whenever we have the two figures, we can estimate the volt. The volt power in watts, W, over the current flow A. So V equals double V in French, of course, W, so that we will not forget, over A. So this is the figure you must memorize. And in the figure, of course, if we apply it, we'll find that the end result giving the volt of 24 volts. Heat production and alternating current. As we said before, we have two types of current. We have the alternating current, as you can see, and we have the direct current. So both currents must be correlated to each other regarding the heat. So whenever I want to compare both of them, I compare it regarding the heat. So I'm trying to create, instead of sine wave, I shift this sine wave into a straight line like the direct current, so I can compare both of them. So we use what we call RMS. RMS means that the current, first of all, whenever it's been doubled, the alternating current will be straightforward to it. And then when we create the mean of it, we get this line. And then when we square it, we get this line. So this line is being compared with the direct current, in where we can compare both current. In the United Kingdom, of course, the current is 240 volts. So this volt creates a heat like that of the direct current of 240 volts. The point is that the alternating current has a peak, and this peak stays for a little while, creating less heat. So this is the difference between the direct current. The direct current all over creates the heat. So this is a way to compare both of them, and we are trying to get them close to each other by using what we call the root mean square. Heat protection and fusion. Of course, this, whenever current passes, as we said, it creates heat and light. This is how we use it as light. So this energy produces is used to create fuses. Of course, when the current is increased much, this fuse will be cut off. Surgical diathermy, as we can see, is made of two plates. First of all, our two electrodes. We have the active electrode held by the surgeon. I have the neutral electrode, as you can see, covering a large area of the patient. So the current goes through one pole, and then it goes creating the heat and the coagulation, and the current must escapes through the neutral place. So it is not an isolator, as we keep saying in the opposite. No, it is a conductor. So this conductor goes back to the circuit where it has been airshed. This is how the current goes through the patient and creates the heat of coagulation. So why doesn't it create the contraction and the ventricular fibrillation that occurs in alternating current? Because the frequency is being much increased. It increased from whenever it becomes 1 kilohertz to 1 megahertz. This current has a high frequency, which will not create the ventricular fibrillation effect, but it will create heat. Of course, the hazards that may occur is why whenever I tell you why this neutral plate does not cause heating of the patient, because it's been covering a large area. This is correlated to what we call the current density. The current, as we can see, spreading all over a large area. So whenever this plate is being detached from the patient, or a small area only is touching the patient, this current will be concentrated in this area, increasing density, causing burn. On the other side, if it is completely detached, the current must escape. Even if the surgeon is not using it, it must go through any part. So suppose through the ECG, suppose of the prosthesis present in the patient. Of course, it creates less resistance. This causes, of course, burns, especially if the patient, of course, is touching an earthed equipment as a lamp, especially if he uses his finger. Of course, fingers has a very low surface area, liable for the current to cause burning. So all these are the hazards of using the monopolar, as we call it. Of course, if we use a capacitor, as we can see from this figure, this capacitor, of course, creates another way of transfer of the current. Of course, the capacitor is much incorporated with high frequency and low frequency of the 24 milliampere of the 50 or 60 hertz used as alternating current in most of the circuits. We have another way to avoid this defect from the detachment of the neutral electrode is using by what we call the the bipolar. Bipolar, as we see, as we know, as it has two parts. These two parts, the electrical charge goes through one and returns back to the other. You see, this needs not to use, of course, the neutral plate. Properties of electrical composite will be shown in the next slide. Capacitance. Capacitance was the meaning of the ability of the object to hold electric charge. In the SI unit, it's coulomb. You see C. The coulomb is the quantity of electrical charges which passing a point when the current is 1 ampere. Of course, as we said before, that the current of 1 ampere equals a special figure, as you can, 6.24 times 10 to the power of 18. When this is in 1 second, suppose we have it in 2 seconds, 3, can we multiply by 3? The defibrillator, it's a device that controls the fashion of the released energy. You see, it's the key point of it is the capacitor. The capacitor means that two conductors separated by air or a dielectric equipment, which does not transfer electricity. Its maximum setting potential whenever I apply volt across this capacitor. Of course, it accumulates charges. So when we apply 5,000 volts across the two plates, it creates amount of charge in this capacitor of around 160 millicoulomb of charge. So these two figures ought to be remembered in the example. So we have a power. So whenever I want to measure the power, I multiply the energy in joule, as we can see, time the current. So if W equals joule per second, ampere. So these are the figures being used to reach to the final estimation that the joule of the energy equals the current per and the volts. By integration, in the new book, we can see this the examples of the integration. We can reach to the stored energy by this 5,000 volt creates an amount of electrical charge of 160 millicoulomb. This needs an energy for this currents to move. So whenever I want to estimate the store, by integration, I have the stored energy. I have to have the stored energy time potential. So in the example, we will get that the final result is 400 joule, and this nearly the amount of us to use in such a defibrillator. We use always 360 watt. Of course, we use the electrodes, one on the sternum and one on the area of the heart. This defibrillator creates 35 ampere for 3 seconds to return the normal SA node effects. Of course, indeed, this defibrillator we have an inductor. Inductor is, as we said before, is a wire. You see, this wire creates an optimum shape and duration and absorbs some of the energy released from the capacitor. This means that not all this energy is being transferred to the patient. Of course, when we use internal defibrillator, we use around 100 joule. Of course, whenever there is supraventricular dysrhythmia apart from sinus tachycardia, we can use, of course, the defibrillator or what we call DC shock to reverse this dysrhythmia. But we must be clear that this transfer must the charge must be transferred after 15 milliseconds of the R wave. Otherwise, if it's been transferred during the T wave, it will create the what we call ventricular fibrillation. Of course, this is a monophasic defibrillator where the current goes in one direction. Nowadays, we have the biphasic, which the electrical charge goes in one direction, comes in other direction. Of course, this saves energy and saves much injury to the human being. So this is commonly used. Electrical charge, of course, the capacitor is not the only way to safe charges. We have, of course, the bobbin. As we know, whenever it causes friction in the tube, it creates electrical charges. These charges are also collected and can induce flammability or origination of inflammable anesthetic. Capacitance, when direct current, of course, goes to capacitor, it is liable for it to collect this charge. And after that, it releases in a controlled fashion. This is what happens in the defibrillator. But the direct current, whenever it goes up, it's been collected till it's fully charged, but it dies away. This is the difference between the two types of current. Of course, this definition of capacitor, we can know why do we have defect in the ECG tracing whenever we have a bulb of the, as we can see from the figure, a bulb of light. This bulb, of course, carries a current of 50 hertz volt, and it's creating as if it is a part of the capacitor, a plate, and the patient is the other place. So the area in between is vacuum. This creates a capacitor. So this current going through the patient on ECG will cause the defect, as we can see in the tracing of the ECG, or what we call interference. It obscures the recording. Of course, this transducer, as we said, it can be used in the measurement of pressure. Of course, we have the pressure has a diaphragm. So the pressure, whenever changes the diaphragm positioning, this goes to a transducer, which is being affected, and accordingly, it will measure the pressure. Inductance and interference. Of course, this is another way how do inductors, this is a transformer, this is the how does the transformer look through, as we have coil and 3 dashes upwards, and another coil. This magnetic field with the electrical equipment causes interference. So this is what we call inductive coupling. So there is a coupling between the equipments by the inductor. Of course, this inductor means a wire coil which creates a magnetic field. We have what we call screening. Screening, this is a method to avoid this interference current, where the electrodes, suppose the ECG electrode is being covered or surrounded by a woven metal. This woven metal is attached to the air. So whenever there is interference, this current will go through this woven material. This woven material is a special material and not affecting the final result of the ECG. And this is the difference between what we call a single and noise. Single is the normal configuration. Noise is the distortion, as you can see. So whenever I want to define, I define it in noise or sound, and I'm sorry. Sound and noise ratio. Of course, to avoid this ratio, and attach it to a galvanometer in the middle, as you can see. This is also attached to a source of current, direct current, as you can see. So we have two resistance, R1 on R2 equals R2, R3 on R4. At this point, the galvanometer will read 0. This is what we call the null deflection, or the balanced circuit. So whenever this R equal, as we can see from it is balanced. You see, this is what we call the null resistant or the null system. You see, suppose I want to measure a pressure. This is in the R4, as we can see. This pressure being introduced will defect the galvanometer pointer. Of course, will change. So how can we return it to a null deflection? By changing the resistance of R3. This is what we call it a rheostat. So we change till this deflection is being returned to a null deflection. At this point, we can measure this resistance. Another way is, as we can see, different resistors are attached to each other, and there is a potential. Of course, this potential will be different by moving, suppose, to 80% of it or 20% of it. So the change in the potential among these four figures or three figures, I'm sorry, we can, if we shift one of them, as we, of course, these resistors are completely equal, and if one of them is a resistor where I want to measure, it can, of course, measure this unknown resistor. Impedance is a resistor, but it is correlated to the frequency. Of course, resistor alternating current does not vary much with the frequency of the current. A capacitor can transmit, of course, alternating current, but high frequency current passes more easily. With the inductor, the reverse occurs. You see? Of course, the unit of impedance also is ohm, but it's ohm, I'm sorry, and it's expressed by Z capital. Of course, skin impedance, of course, whenever I put the electrodes, these electrodes may not transmit charges if they are not full with gelatin, or they are partially detached from the skin. On the other hand, the monitor resistor being high, this will distort the signal reaching to the patient. On the other hand, if I have a strong or a high resistor of the monitor and a low resistance of the electrode, you see, it gives me much better a signal. Of course, the skin impedance is lowered when there is skin moist. Skin moist, of course, means sympathetic activity. So this is a method to measure the sympathetic activity in the human beings. And these are some questions. Of course, these are the figures denoting the electrical components. We have the capacitor, as you can see, and we have an inductor coiled, and then we have the resistance, and then we have the battery, and then we have a diode, and then we have an earth, and this is the amplifier, the triangle, and then we have this the shift, and this is the form of the amplifier. I'm sorry, the transformer. Of course, the rectifier is a device to shift from direct current to alternating current.